Hello there. Today we are going to learn about the speed of light and time dilation and how all that stuff works using the example of a rocket ship traveling throughout a period of time in space. So the speed of light that we're going to be using, it is very close to 3 times 10 to the 8 meters per second. It's just slightly under that in reality, but it's easier to use a round number, so we are going to for this purpose. The situation we're going to be considering is moving from planet A to planet B on the very poorly constructed SS Ukraine, and we are an observer watching this travel take place on planet C. So we're kind of beside the spacecraft, so it's going to kind of fly by us at some point. So this could be something like moving from Earth to Pluto, and we're sitting on Saturn or something in the middle here and watching this take place. So, as I've mentioned before, if we have a clock on planet C and we have a clock on the ship, depending on the speed of the ship, the observer on planet C is going to see the clock on the SS Ukraine actually move at a slower rate than their own clock, and that will slow down the more that the speed increases. Whereas the people on the SS Ukraine will not experience any more time. They will think everything is moving completely normally, and if they were to look outside to see, they would actually see that moving at a different rate. So a clock, we're traditionally thinking of a watch or a clock on a wall or some sort of repeating pattern. But all that's really required for any sort of clock or timekeeping is something that will consistently repeat at the same speed, the same duration over and over. So atomic clocks use like a cesium atom. The type of clock that's in a well-made watch is a crystal that vibrates. So it's something that just operates back and forth at a very predictable rate. So we are, for this purpose, going to make up a hypothetical clock that is based on light, called a light clock. So at the bottom here, we're going to have a mirror with an emitter that will shoot out a tiny packet of light towards a mirror on top, and then that will bounce back, hit the mirror on the bottom where there's a little detector that will then shoot out another packet of light. And it will just do this over and over, therefore moving completely vertically as far as you're concerned on the ship, and the light packets will just move obviously at the speed of light towards the top mirror, bounce off of it, hit the bottom mirror, another packet will be released over and over and over again for the entire time. So each one of those round trips is just a tick. For our purposes, we're going to say that a tick takes 1 second. In order for that to really be the case, this would have to be 300 million meters wide, but we're just going to pretend that's the case because, again, it avoids a lot of decimal places. So one fundamental thing in all of this is that the speed of light at any reference point in the universe, no matter how fast you're going, no matter where you are, the speed of light must be the same to everybody. They will all view it as happening at the same speed, no matter what speed you are actually going at. So unlike a thing like a baseball, where if you're in a car and you throw it forward, it's going to then move at a different speed because of the speed you're already going. That doesn't happen with light. Light does not kind of gain momentum or something based on the ship or whatever. So it won't change no matter what reference frame you're in. And to make that kind of make sense, things that we think of as not moving are moving. Nothing in the universe anywhere is actually not moving. It's only potentially not moving compared to another thing. In other words, everything is relative. So something orbiting Earth is also moving through Earth's orbit, and the sun is also rotating around a cluster of stars, and the galaxy is also rotating, and the galaxy itself is moving around a bigger cluster of galaxies. So there's so many speeds that you can never really know an absolute speed that something is at. It's only relative to another thing that you can actually judge a speed based upon. So as far as you're concerned on the ship, you're going to see this moving completely vertically up and down. If you were to stand in front of it, it's just going to move up, down, up, down, up, down, over and over for your entire journey. However, if you are on planet C here, and you were to view this rocket moving by at a speed of 10,000 meters per second, which is very fast, but still nowhere near as fast as the speed of light itself, you're going to see it not move completely vertically up and down, but move up and down with a little bit of horizontal movement to it as the ship moves from planet A towards planet B. So that's going to create a little bit of a zigzag, very slim triangles at this amount of speed as it moves in that direction. So from your perspective, the light is actually going to seem to travel a little further than it would if you were actually on the spaceship itself. So at a high but still relatively low speed here, you're going to have very thin segments to these triangles. However, if you get to this point where you're at half the speed of light, you're now going to see pretty wide gaps between what the people on the spaceship are going to see. So instead of seeing it vertically, you're going to see it actually stretched out and creating diagonal lines completely up and down. So that will stretch out. And that's where the Protagonist Theorem comes into it. Because of this, depending on the speed that the spaceship is traveling, we're going to see triangles that have kind of different shapes and dimensions to it. The sides of these triangles are going to be looked at from both inside the spaceship and on the planet externally. So on the spaceship, you're going to see the amount of time that it takes for the beam of light to hit the top and come back down to the bottom as the speed of light, which is represented as c, times x. So whatever x happens to be here, whatever that distance is. For our purposes, we're going to end up saying that's just 1 second. So it takes 1 second to do a round trip here, and that's the time that it takes. The external observer is going to view that it moves along this diagonal line at a rate of the speed of light times whatever amount of time that takes for them. And this horizontal line is going to be the velocity of the ship over whatever amount of time it requires to travel this diagonal line. So inside the ship, Cx is going to be our reference of time, or how fast we think it is. In this case, we're going to say 1 second. This is the amount of time that it's going to appear to a person on the outside. So using Pythagoras' theorem, we know that cx squared, since this is a right triangle, cx squared plus vt squared is going to equal ct squared. So if we take that and start to rearrange it using a bunch of algebra stuff, we can distribute all the squares to everything. We will then take everything, divide it by c, so eliminating the term there, eliminating the term there, and then putting the last term over c. We can then swap out the x to the outside of our equation. We've already decided that x is going to be 1 second. But t, we don't know. We're looking for t ultimately. So we're moving x out to this side. Everything here is now dandy and squared. We're then going to distribute out. So we've got a t squared in here, t squared in here. We're going to take that out and have them both be distributed outside the outside the brackets itself. So we've got 1 minus the velocity squared over the speed of light squared. And then we're going to flip this x and t back so that we're actually solving for the t side of things. So t squared equals x squared divided by 1 minus v squared over c squared. And when we get rid of the square roots here off of everything, we're just going to square root everything. Getting rid of these exponents, we're going to end up with t equaling x divided by the root of 1 minus v squared over c squared. So x being the amount of time that someone on the spaceship sees it as going up and down, which we're going to say is 1 second, divided by the square root of 1 minus the speed of the ship squared divided by the speed of light squared. And the way that works out into the real numbers will be this. So we've got the speed of light, as we said, at 300 million meters per second. The velocity of the ship in the first example is going to be 10,000 meters per second. And we're saying one of these ticks is going to take 1 second. So what is the t? What the person on the ship is going to view 1 second. What is the amount of time that someone outside the ship is going to view that as taking? So as we plug the numbers in here, obviously they're fairly big ones, but as you finish this out, you're going to get t equals 1 over 0.9999, etc., a very close to 1 number. When you work that out, you're going to get 1 bunch of zeros and a little bit. In other words, at a very high speed of 10,000 meters per second, a year on the rocket is only going to appear to be 1 year and 1/10 of a second to someone standing on planet C. So again, because the speed of light must always be constant no matter where you are standing, the fact that when we see that light go diagonally while someone on the ship sees it go straight up, the diagonal forces it to go a little bit further. The only way to reconcile those two things is to actually cause our perceptions of time to be different. The observer on the planet must view time in a slightly different rate than the person on the ship. They see it going at 1 second. In other words, it's taking 300 million meters to go that 1 second, whereas someone on the outside is going to see it go farther than 300 million meters. Therefore, it must be slightly larger than 1 second. So they're going to see a stretched time, or the person on the rocket has a compressed time, depending how you view it or which one is you. So as we go a lot faster now, we're going now at half the speed of light. Everything else is staying the same. We're still dealing with 1 second. We plug in the 150 million meters per second here, and now we're going to get 1 over 0.866025. So we're going to get an approximate 15% increase in the amount of time. 1 year on the rocket, 1 year of what you perceive to be a year on the rocket, is going to actually look like a year and 2 months on the outside of the rocket, on the planet that we're sitting at looking. So a way to say this again is the time has taken 15% longer, but also the distance that the light has to have traveled from the outside, the way that they see it, is 15% bigger. So it's actually traveled 15% farther because it's moving up, down in the diagonals as opposed to straight up, down. And since speed of light must be the same, it must take 15% longer. There's no changing the speed of light itself. Now, as we get really close to what the speed of light itself actually is, here we're going to be like 99.7% of the speed of light. We're going to get to amounts where we got 1 over 0.08. In other words, 1 year on the rocket will now feel like 12 years and 3 months outside the rocket. So if you're on the thing moving from planet A to B, everyone on planet A, B, and C are going to think it takes 12 years. You're only going to experience 1 year of your time. This then starts to get very, very exponentially higher as we go closer and closer to the speed of light. So this is already quite close, but now as we add in 299,999,000, we're now at 99.9999% the speed of light. Once you put it in through the same equation, we're now getting that 1 year on the rocket is 387 years on any of the planets observing you from a stationary point of view. They will see that it took you 387 years to get there, but you're only going to experience 1 year if you're actually the person on the rocket. So you can see as we're adding just a little bit more, it's starting to get so insanely exponentially higher. And when we hit the final point that we're now going at the speed of light, which is obviously impossible, but say that we can do it, we end up with the equation working this way: 1 divided by the root of 1 minus the speed of light squared over the speed of light squared. So in other words, 1 divided by the root of 1 minus 1. 1 minus 1 is 0. The root of 0 is 0. And therefore, the time you would feel is 1 divided by 0. And since you can't divide by 0, it's not possible to do that, it's an undefined number, that's where it completely breaks down. So you could, at this point, be on the rocket traveling at the speed of light for an infinite amount of time, and you would feel no time. So that's the reason that it works that way. So no matter how long the trip is, how long the trip would appear to everyone on the outside, if you were actually on the ship that was traveling at this speed, you would experience no time whatsoever. And when an observer was looking through the window, instead of at this point seeing that you had a beam of light bouncing up and down or bouncing diagonally, they would just see a dot of light moving completely horizontally. It would never move up and down to them because no time is passing. They would literally just see the speed of light moving completely horizontally across the horizon, moving from A to B. So they would see it moving, again, at the speed of light. And the only way for them to see it moving at the speed of light is if you, on the rocket, were not experiencing time at all. It could not be moving up and down, because if it was moving horizontally at the speed of light and it was moving vertically with any velocity whatsoever, then it would be moving faster than the speed of light, which is not possible for light to do, since light by definition moves at the speed of light. So that's why you get there. That's why it's impossible anyway. But if you were able to actually ever be in that reference frame, you would experience time as a total stop. It would be instantaneous. It would never happen. But that is why that's not a possible thing. So that was kind of fun to put together. I hope that's a decent explanation. I think that's like the easiest way to conceptualize it. There's other things that are actually involved here in terms of actual space stretches. The rocket ship actually physically gets bigger, and the space between A and B actually shrinks. So another way to consider it is that as you approach the speed of light, the actual size of yourself expands and the size of space between 2 points contracts, such that when you hit the speed of light itself, point A, B, and C, and the rocket are all at the same place at the same time. Every point in the universe would be at the same place at the same time. But that's much more complicated to get into. So I hope kind of the triangular level of thinking makes a little bit more sense. And good luck getting to Planet B on a former Soviet craft. Bye.